Have you ever pondered about the origin of supermassive black holes? Those mysterious cosmic monsters that lurk in the heart of galaxies, including our own Milky Way? Supermassive black holes are an enigma that have puzzled scientists for decades. These cosmic giants, millions to billions of times more massive than our Sun, sit at the heart of nearly every galaxy. Yet, despite their omnipresence, they remain shrouded in mystery and intrigue. Why? Because their existence seems to contradict our current understanding of the universe. They are simply too massive to have formed from the collapse of a single star, the process that creates smaller, stellar black holes. So how did they come into being? What could possibly lead to the formation of such colossal entities? The answers remain elusive, but scientists have proposed a number of intriguing theories. Let's dive into the top 10 theories that attempt to unravel this cosmic mystery. Imagine a massive primordial gas cloud hovering in the early universe. What if this was the cradle of supermassive black holes? Such is the premise of the gas cloud collapse theory. Picture, if you will, the universe in its infancy, filled with colossal clouds of gas. These aren't the fluffy white clouds we know from our earthly perspective. Instead, they are dense, swirling mists of hydrogen and helium, the raw materials of stars and galaxies. The theory proposes that these gas clouds could have been the birthplaces of supermassive black holes. How, you may ask? Well, it's all about gravity. The immense mass of these clouds would have created a powerful gravitational pull. Over time, parts of the cloud would start to clump together, growing denser and denser. As these clumps grew, so did their gravity, pulling in more and more gas. Eventually, the center of these clumps would become so dense and the gravitational pull so strong that nothing could escape it, not even light. In essence, a black hole was born. But not just any black hole, a supermassive black hole. These behemoths are millions, sometimes billions of times the mass of our Sun, and they could have sprung from the collapse of these primordial gas clouds. While this theory provides a plausible explanation, it isn't the only one. What if black holes could form directly without a stellar precursor? Welcome to the direct collapse theory. This theory suggests that under incredibly specific conditions, a black hole can form directly from a gas cloud without going through the usual star life cycle. Think of it as skipping a few billion years of stellar evolution and jumping straight into the black hole phase. Firstly, let's look at the conditions needed for this event to occur. The gas cloud needs to be extremely dense, about 1,000,000 times denser than the interstellar medium. Also, it should be almost entirely devoid of any elements heavier than helium. This is because heavier elements tend to cool the gas cloud, allowing it to fragment and form stars instead of a black hole. Another critical factor is the presence of intense radiation. This radiation prevents the gas cloud from cooling down and fragmenting. Consequently, the cloud collapses under its own gravity and forms a black hole directly. The direct collapse theory has been gaining traction in recent years. It's a fascinating idea that could potentially explain the existence of supermassive black holes in the early universe. After all, these cosmic beasts are too massive to have formed from the remnants of first-generation stars. However, the conditions required for direct collapse are so specific and extreme that some astrophysicists question whether they could have existed in the early universe. This theory might sound compelling, but it's not the only contender. Picture a cosmic dance of doom where smaller black holes merge to form a supermassive one. This is the essence of the merging black holes theory, a captivating idea that proposes the existence of supermassive black holes as a result of smaller black holes combining over billions of years. The dance begins when two black holes, caught in each other's gravitational pull, start to orbit one another. As they spiral closer and closer, an inevitable collision course is set. This is no ordinary collision, it's a cataclysmic event that sends ripples through the fabric of space-time itself, an occurrence we recognize as gravitational waves. The result of this grand collision? A larger black hole is born, its mass equivalent to the combined mass of the two original black holes. It's a process of cosmic cannibalism where black holes consume others and grow larger in the process. This theory is particularly fascinating because it provides a plausible pathway for the formation of supermassive black holes in the early universe. These colossal entities, millions or even billions of times the mass of our Sun, are thought to have formed relatively quickly after the Big Bang, and the merging black holes theory offers a way to explain such rapid growth. But like all theories, it's not without its challenges. The key lies in detecting these merging events and studying them, a task made difficult by the elusive nature of black holes themselves. As fascinating as this theory is, there are still more theories to explore. What if the secret to black hole growth lies in the winds of stars? Introducing the stellar wind accretion theory. This theory takes us on a cosmic journey where black holes are not just destructive forces but entities that grow and evolve, fueled by the very stars they often devour. Here's how it works. Stars, particularly those significantly larger than our Sun, emit what's known as stellar winds. These winds are streams of charged particles, essentially the star's outer layers, propelled into space by intense heat and radiation pressure. Now imagine a black hole lurking nearby. It's close enough to feel the push of these stellar winds, but far enough to avoid swallowing the star whole. The black hole's formidable gravitational pull begins to capture the material from these winds, drawing it into a swirling disk of matter known as an accretion disk. Over time, this stellar material falls into the black hole, leading to its growth. This is the stellar wind accretion theory in a nutshell. It proposes a fascinating possibility. A black hole's size may not merely be the result of catastrophic events, but could also be the product of a gradual, almost parasitic feeding on the winds of nearby stars. And the best part? This theory isn't purely hypothetical. Observations of high-energy X-rays from certain black holes suggest that stellar wind accretion could indeed be a reality. As we delve deeper into these theories, the mystery only seems to intensify. Could dark matter, the universe's invisible mass, play a role in the formation of supermassive black holes? This is the dark matter halo theory. Let's delve into the enigma of dark matter. This elusive, invisible substance is believed to make up about 85% of the universe's mass. We can't see it, touch it, or detect it directly, yet its gravitational effects on galaxies and cosmic structures are profound. So how does this relate to the formation of supermassive black holes? The dark matter halo theory suggests that these invisible halos of dark matter could be the cosmic cradles where these black holes are born. Here's how it works. Dark matter halos are thought to form around galaxies, creating a gravitational pull that attracts regular matter. As this normal matter congregates and compresses under gravity, it heats up, eventually becoming so dense and hot that a black hole is born right in the heart of the halo. It's like a cosmic pressure cooker, where the ingredients are dark matter and regular matter, and the product is a supermassive black hole. This theory gives dark matter a significant role in the universe's drama, making it not just a silent, invisible actor, but a powerful director shaping the cosmic stage. However, like all theories, the dark matter halo theory has its critics, and is one of many attempts to solve the mystery of how supermassive black holes form. As we venture further, the theories become even more intriguing. Could supermassive black holes be relics from the Big Bang itself? Enter the primordial black holes theory. This theory suggests that supermassive black holes are ancient entities, formed in the universe's infancy. In the first fractions of a second after the Big Bang, the universe was a hot, dense soup of particles. If the density of this primordial soup varied enough, denser regions could have collapsed under their own gravity, forming black holes. These are what we call primordial black holes. Unlike their stellar cousins, which are born from the explosive deaths of massive stars, primordial black holes are unique. They could have formed from pure energy, without needing a star as a precursor. The theory also suggests that these black holes could have grown supermassive by merging with other black holes and consuming matter over billions of years. This would explain why we observe supermassive black holes at the hearts of almost every galaxy, including our own Milky Way. However, as intriguing as this theory is, it's not without its challenges. For one, we've yet to detect a primordial black hole. Also, the conditions required for their formation in the early universe are extremely specific and not entirely understood. Yet, the primordial black holes theory remains one of the leading ideas in the quest to unravel the origin of supermassive black holes. It's a fascinating thought, isn't it? That these monstrous cosmic entities could be as old as the universe itself. The cosmic mystery deepens with each theory, doesn't it? What if supermassive black holes started as seeds growing over billions of years? This is the black hole seed theory. Imagine a supermassive black hole as a giant tree, and like any other tree, it had to start from a seed. In this context, the seeds are small black holes formed in the early universe. These seeds then grow over time, feeding on the surrounding gas, dust, and even other stars and black holes to become the supermassive black holes we observe today. These seeds are thought to have been created from the remnants of massive stars that collapsed under their own gravity. They were then left to grow in the heart of galaxies, feasting on the abundant material available. This growth process wasn't slow, however. It was a highly efficient, fast-paced feeding frenzy fueled by the extreme conditions of the early universe. However, this theory isn't without its problems. For one, the universe was a much different place billions of years ago. The gas was denser, and the stars were more massive, making it difficult to explain how these seeds could have survived long enough to grow into the behemoths we see today. Despite these challenges, the black hole seed theory provides a compelling explanation for the origin of supermassive black holes. It's a captivating concept, isn't it? A tiny seed growing into a cosmic monster, shaping galaxies and bending the very fabric of space-time around it. The enigma of supermassive black holes continues to perplex us. Could quasars, the brightest objects in the universe, hold the key to the origin of supermassive black holes? Welcome to the ninth theory, where we delve into the fascinating realm of quasars, those celestial bodies that outshine galaxies, and their potential connection to the formation of supermassive black holes. Quasars, short for quasi-stellar radio sources, are the most powerful objects in the universe. They are so luminous that they dwarf the brightness of their host galaxies. But what makes them so intriguing in our quest to understand black holes? Quasars are powered by supermassive black holes at the center of galaxies. As matter spirals into these black holes, it heats up and emits enormous amounts of energy, creating the brilliance we associate with quasars. This process, known as accretion, is what fuels a quasar's luminosity. So could the existence of these quasars give us insight into the birth of supermassive black holes? The Quasar Theory suggests that the intense energy emitted by these quasars could play a role in the formation of black holes. This energy might trigger a series of reactions, leading to the condensation and eventual collapse of matter into a black hole. However, like the other theories we've explored, the Quasar Theory is not without its challenges. It still grapples with explaining how these black holes could grow so massive in such a short cosmic time. As we approach the end, the theories only become more captivating. Could the collision of galaxies lead to the birth of supermassive black holes? This is the Galactic collision theory. Picture two galaxies, each with their own central black hole, spiraling in a gravitational dance. As these celestial giants draw closer, their gravitational forces begin to interact, pulling and tugging at one another. The galaxies, stars, and gas clouds are swept up in this cosmic ballet, creating a swirling spectacle of light and matter. This is where the Galactic collision theory steps in. According to this idea, when galaxies collide, their central black holes can also merge. This cataclysmic event sends gravitational waves rippling through the fabric of space-time, a phenomenon predicted by Einstein's theory of general relativity and confirmed by observations in 2016. As the black holes draw nearer, they spin faster and faster, creating a vortex of energy and matter. Eventually, they become one, birthing a supermassive black hole in a brilliant explosion of energy. This is not a quiet event, it's a cosmic crescendo, a grand finale to the gravitational symphony that began with the galaxy's first approach. The Galactic collision theory offers a tantalizing possibility for the creation of supermassive black holes. It's a reminder that the universe is not a static place, but a dynamic, ever-changing stage where galaxies pirouette and black holes form in a celestial waltz of epic proportions. Each theory is a piece of a cosmic puzzle that we are yet to solve. As we've seen, the origin of supermassive black holes is a topic of intense debate and study. Each theory we've explored, from the collapse of massive primordial gas clouds to the merging of smaller black holes in the early universe, offers unique perspectives on the birth of these cosmic giants. And who can forget the intriguing possibilities presented by the stellar wind accretion theory or the dark matter halo theory? Even the thought of black holes born from galactic collisions or the seeds of black holes offers much to contemplate. Yet the mystery persists, and the search for answers is far from over. Scientists and researchers worldwide continue to delve into the enigma of these supermassive black holes, employing cutting-edge technology and innovative thinking to unravel the secrets of the universe. While we may not have definitive answers yet, the quest to understand the universe continues. And isn't that what makes astronomy so fascinating? Before we wrap up, we want to remind you that you too can be part of this cosmic journey. By liking, commenting, and sharing our videos, you help us reach more people who are as fascinated by the universe as we are. It's a small act, but it's one that can make a big difference. If you have more theories or thoughts on the origin of supermassive black holes, we'd love to hear them in the comments section. Your insights and curiosity help fuel our exploration of the cosmos. And remember, subscribing to our channel ensures you never miss a moment of our journey through the cosmos. Each video is a new expedition into the unknown, and we can't wait to share more with you. Together, let's continue to unravel the mysteries of the universe. So hit that like button, share this video with your friends and family, and let's keep exploring the cosmos together. Thank you for being a part of our community of cosmic explorers. Until next time, keep your eyes on the stars.